Remember, we said we needed search, not just learning, because we want to solve complex problems that require thinking and reasoning. We defined what a search problem was. Remember, we had this simple tram example where we have a certain number of locations, in this case 6, and you're trying to go from 1 to 6 by either walking or taking a tram. We can define the search problem formally by defining a start state, a set of successors, which are actions that you can take from each state. Each action has a cost, and each action also takes you to a subsequent state. And then finally, there's a test that takes a state and returns whether we're at the end or not. And the objective in a search problem is to find a solution that minimizes the total cost, which is the sum of the cost of all the actions. Okay. Last time we saw 4 different algorithms. We saw 2 exact algorithms, doing exhaustive search or doing dynamic programming, which is essentially exhaustive search with caching. And remember, we framed exhaustive search and dynamic programming as computing future costs, which is the minimum cost way to go from each state to an end state. And then we looked at approximate algorithms, best of n, which just samples a bunch of solutions independently given some policy and takes the best one, as well as beam search, which builds up this kind of beam of possible solutions and taking the best and truncating at each point in time. Okay, so that's a review of what we did last time. So this time, we're going to continue doing exact algorithms, but we're going to explore search problems that have cycles in them. We're going to look at 2 types of algorithms, uniform cost search and A*, which is, we'll see that is actually UCS in disguise. Okay, so let's begin with uniform cost search. So to motivate this, I want to step back and think about these 2 idealized mathematical concepts in search. So the first we already saw last time, which is future cost. So this says, from a given state, what's the best way to reach an end state? And then you can also define, analogously, a past cost, which is the minimum cost solution from the start state to that state. So here's a picture you should have in your head. If you're at a particular state, you can look backwards, and you can look, that gives you the past cost. What is the best way to go from start to that state? And you can also look at future cost, which is the best way to go from that state to an end. So each state has a past cost and a future state cost. Okay? And of course, if you have future cost plus past cost, that gives you the best solution that goes through a particular state. All right. So in dynamic programming, we computed the future cost for each state using a recurrence. And what you notice is that future cost of a particular state depends on the future cost of its successors, which means that you need to first compute the future cost of all the successors before you can compute the future cost of a state. So when you run dynamic programming, it's written as a recurrence. But if you look at the ways in which the cache is populated, you'll essentially start from the end, and you start computing future states until you reach the start state, and then you're done. So this might seem a little bit familiar. It's actually very similar to what we did in backpropagation, where you start at the end, and then you compute backward gradients until you get to the beginning. So there's a deeper connection here, but it's kind of the same idea. And importantly, in dynamic programming, you can't have cycles. What happens if you have cycles? You get an infinite loop in code, and mathematically it's just not defined, right? Because the future cost of state depends on state prime and vice versa, then it's just not well defined. Okay. So suppose there are cycles in your search problem. So here is an example. You have 4 nodes in a graph, and here are the edge costs. And these edges are undirected, which means that you can go from A to B, and you also go from B to A, and we're going to assume that the cost in both directions is the same. Okay, so given this, what do we compute first? Do we go A, B, C, D, or A, C, B, D? It's not really clear, right? Because there's no topological ordering of the nodes that makes sense. So what can we do? Any ideas? Okay, it's maybe not obvious. Well, the obvious answer is UCS, but maybe that's not helpful as an answer yet. So UCS, it's also known as Dijkstra's algorithm, which was developed in the 50s. And in UCS, we're going to make a trade here. We're going to say we can handle cycles, but all the costs are going to be non-negative. Okay? There's actually a way also to do negative edge weights as well as cycles. That's called the Bellman-Ford algorithm, which we won't talk about. So there's 2 differences between dynamic programming, which we've seen, and UCS, which we're going to introduce. The first is that instead of computing future costs, we're going to compute past costs. So remember, the past cost of a state is the minimum cost way to go from the start to that state. Okay? And we're also, and here's the key insight, we're going to process the states in order of increasing past cost. Instead of using the graph structure to give us a topological ordering, we're going to just go in increasing past cost. Okay. So here's the high-level strategy of uniform cost search. By the way, who has seen Dijkstra's algorithm or UCS before? Okay, so I think this will be somewhat of a review, but it's important because how many of you have seen A-star before? Okay. So maybe half of you. Okay. So here's a high-level strategy. We're going to look at all the states and partition them into 3 buckets. The first bucket is explored. These are the states we've already found a minimum cost path to, and we're done. The frontier, which is states that we've seen in our algorithm, but we're still trying to figure out the best way to get there. And then finally, unexplored are states that we haven't seen yet. Okay. So what we're going to do is we're going to start with explored just being the start state. And then we're going to kind of expand out into the frontier. And once we explore an end state, then we're done. Okay. So let's go through some examples and walk through a code to see how this works. So we're going to use this very simple search problem. It's going to be defined by this graph that I just showed. So A is connected to B with cost of 1 and to C with cost of 100. And you can just read that. So let me actually draw this on the board so we have a reference. Okay, so we have A, we have B, we have C, and we have D. And this is 1. This is 100. This is 1. This is 1. And 100. Okay? All right, so, and this is what it's a less pretty way, but a more accurate way of representing the state graph. So we define this problem, successors of A, just so we're on the same page. From A, you can take an action to go to B with cost 1 and action to go to C with cost 100. Okay? So let's run UCS on this example here. Okay? So this is the first time I'm going to introduce UCS, but I'm going to walk it through on this example, so hopefully it'll ground things out for you. So remember there is the frontier. We're going to use a priority queue to denote the frontier. And the priority of, so each element in a priority queue is a state, and its priority is going to represent the minimum cost that we've found so far to get there. Okay? And the reason we were going to make a priority queue is, what do you do with priority queues? What can you do with priority queues? Anyone? Yeah?
Always want the minimum or maximum.
Yeah, so you can find the minimum element. Okay, so what we're going to do is to take the frontier and find the state that has the minimum priority, and we're going to move that to explored. Okay, so that's just foreshadowing that. So for each state we've reached, we're also going to have a back pointer that tells us how we get there. So this is technically not necessary if you just want to know the number, which is how the cost of the solution. But in general, you don't just care about the number, you actually want the solution, in which case you have to remember which actions you took to get to a particular state. All right, so in the beginning, we have a start state, and we have a frontier. And the frontier is just going to have one element. This is a priority queue. It says A, I know how to get there with cost 0, which is true. Empty set of actions gets you there. So now I'm going to loop, and I'm going to remove the state from the frontier with the lowest priority. Okay. Later, I'll show you a theorem that says this priority is actually the past cost. So priority is just the mechanics of the algorithm, what's it's being computed. Past cost is a mathematical quantity, which is the minimum cost way to get to a state. Okay, so in this case, the priority queue has only one element, so that's A, and has a past cost of 0. And then what I'm going to do is I'm going to look at all the successors of A. Here's a possible successor. I can go to B. And I'm going to update the frontier. So from this explored, freshly anointed explored node, I'm going to try to reach out to the frontier. Okay, so I can get to B with cost 1, and I'm going to update this priority queue with past cost, which is 0, plus the successor cost, which is 1 here, which gives me a B of 1, which means I can get to B with past cost, with cost 1. And the way we do that is I'm going to represent, keep track of this back pointer, which says the previous state was A, I took action B, that was cost 1, and that's how I got to B. Okay, so that's just remembering the last action. Okay, so here's another successor, C. Has a cost of 100. I do the same. I can update the frontier. Now C, I know how to get there now. Before C was unexplored. Now C is on the frontier with a cost of 100. And I add the back pointer. So I keep track of how I got to C via A. Okay, so now that's all the successors of A. I go back. I look at my priority queue. And I see which one has a lower priority. Should be B, right? So I take B off the frontier. It has a past cost of 1. And then what I'm going to do is look at the successors. So notice I can go back to A. There's cycles, but it doesn't matter because I'm going to try updating the frontier with A, but the A was already in the explored, so I kind of skipped that. And then I can also go to C. So now there's something is interesting. C is already on the frontier. Things that are on the frontier are things that we've visited, but they're not necessarily the optimal way to get there. And here what we've seen is that we're at B with past cost of 1. We can take a successor C with cost of 1, and that means we can go to C with cost of 2. So we update that frontier. So we're not adding new nodes to frontier, we just update its priority. And once we update its priority, we also update the back pointer. So before C was getting there via A, and now I'm getting there via B. Okay, so finally I have action D. So from B, I can go to D, and D is a new node that was unexplored, now it's on the frontier, with cost 1 plus 100, and that's 101. And I also keep track of the back pointer. Okay, so now go back to the top, and let's take the lowest priority on the queue, and that would be C. So with C, I look at places I can go. So I can go to A, but A is already explored. I can go to B, B is already explored. I can go to D, and D, let's see, should I update D? Okay, so D was on the frontier with 101, and now I found a new way. I can go 2 plus 1, and that gives me a way to update D. And now I update the back pointer for D, which says I can go to D via C, and that gives me a cost of 3. Okay, so finally, I empty the frontier. I'm at D. D is an end state. So then all I have to do is, I'm done. I already know I know that I can get to D with cost 3. I just need to walk back the back pointers to reconstruct the steps. So I get the back pointer. I basically, I'm at D. And the last action I took was going to D. And now I go back to C. The last step to get to C was this action. Now I go back to B. And the last action to get to B was this action. Okay? So I can reconstruct that solution, and then I return it. So in the end, uniform cost search produces this solution, which is going from A, which is the start state, to B, to C, to D, and that gives me a cost of 3. Okay, any questions about that? All right, so let's look at some other examples. So here's another search problem. So states are going to be points on a grid, and you're going to be able to move up, down, left, right, and each action costs 1. So here's the grid. Okay, so I have 5 rows and 5 columns, and here S is the start state, E is the end state. Hash means a wall which you can't go through. So it looks like this should be something like this. Okay, so let me just solve normally you can't solve search problems, but this is actually not that hard. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so it should be 14. And here is the uglier but more accurate representation of the graph. Okay, so the start state is 0, 0. Successors from 0, 0 are just going to the right, has a cost of 1. And you can see the reason is that I can't go down because that's blocked off. And then I'm not at the end either. Okay, so let's run UCS on this example. Okay, so I get a cost of 14, and it goes right, down, left, and so on. Okay. So that's just another example. I'll come back to that later. So hold on to that. So here is a nice visual that illustrates how UCS is operating when you have a much larger search problem. So So basically here, here is, if you can see this down here, this dot is the start state. This dot over here is the end state. Each pixel here is a state in general, and actions are just moving consecutively. Essentially, this is essentially the grid problem, but much larger. Okay, and what I'm going to do playing this video is it's going to show the progress of uniform cost search. And what I have here is the explored state. The yellow is the frontier. Everything else in white is unexplored. And you can see this kind of lightning green thing. And that's basically tells me the path to the node on the frontier that I'm taking off. Okay? So as you see, as you run the uniform cost search, you can see why it's called uniform cost search is because it's expanding out kind of uniformly from the origin or the start state. Okay? Because uniform cost search doesn't really know anything about where end is. It's just kind of uniformly trying to find states that are close to the start state. And eventually, you'll get to the end state if your graph is connected. Okay? So hold on to this. We'll come back to this picture when we look at A star. Okay, so I guess we can go a little bit farther, and eventually it will get to the end. There you go. Okay. All right. So that's how uniform cost search works. Now let's revisit one important property here, which is I made some sort of hand-wavy claim that the priority that was computing uniform for cost search was actually the past cost. In other words, is this actually compute the minimum cost path? And this is going to be it's a proof, but it's hopefully is a short proof. And remember, all the costs have to be non-negative, otherwise it doesn't work. And intuitively, you can see why this assumption is necessary for the algorithm, because the idea is that I have this explored set, which I'm growing out, and I'm sort of declaring, without seeing anything else, that the explored set is the optimal way to get to a node. Now, if you have negative costs, you can essentially maybe go out very far and get like a negative 1,000,000 and then come back. And that UCS obviously wouldn't detect that. But if all the costs are non-negative, that can't happen because going out far is just going to only increase your costs. Okay, so here's the theorem. So suppose that UCS moves a state from the frontier to the explored set. Then I'm going to claim that then the priority of S is equal to past cost. Remember, priority of S is what's computed by the algorithm. And past cost is mathematically defined as, in the search problem, the minimum cost path of getting to S. Okay? So if you could show this, then you're done, because this holds for all states, in particular an end state. And once you get to end state, then when you pop that up, if that actually gives you your past cost, that's the best way to get to the end state. So let's prove this by induction. So the base case is priority start equals past cost equals 0. Okay? Done. Because at the start, priority is 0 and past cost is 0. So there's nothing to say there. Okay, so now I'm going to assume by induction that this property hold, priority is actually past cost for everything in explored. And then I'm going to show that this additionally will hold for the S that I removed from the frontier and put in explored. So remember a proof by induction. If I have the inductive hypothesis, then I just kind of iterate this and it holds for all S. Okay, so in particular, when I look at S, there is some path from start to S. And there has to be, because otherwise I wouldn't have found out about S. I'm going to call that the blue path, which corresponds, and the cost of that path is the priority of S. Now, in order to show that this is actually the path of past cost, I have to show that any sort of alternative way to get to S is not going to be better. It might be the same, but in general, it's going to be worse. Okay, so I'm going to call that the red path, and it goes through, and without loss of generality, it starts at start, it goes to some, its start is in explored, S is not in explored, so it has to cross over at some point. So let's suppose it crosses over this bridge from T to U. U could be S, for example, T could be start, but in general it looks like this. And I want to show that the cost of this red path is at least the cost of the blue path. And if I can show this, then I'm done. Okay? So there's a few inequalities here which we'll just step through. Okay, so let's look at the cost of the red path and try to lower bound it. So the cost of the red path is at least the past cost of T plus the cost from T to U. Okay? And why is this? It's because past cost of T is the minimum cost of T. So that is going to be smaller, or at least no larger than whatever random red path you took to get to T. Okay, and also from U to S, because all costs are non-negative, this is, I can just throw it away and make this number smaller. Okay, so now by the inductive hypothesis, past cost of T equals priority of T because T is explored. Okay, so the next step is I'm going to say this is upper bounded by priority of U. So the reason is when T was added to the explored set, some time ago. And at that time, I remember when you add something to explored, you go check out the frontier, or you look at successors. And therefore, I would have updated, if T is connected to U, I would have updated the priority of U with this number, priority of T plus cost of TU. Which means that whatever is in the priority of U has to be no larger than that. Okay? All right, so priority of U is larger or equal to priority of S, because I chose S over U to take from the frontier. I always choose the smallest priority from the frontier. And then the priority of S is, by definition, the cost of the blue path. Okay? So I've shown that the cost of the red path is at least equal to the cost of the blue path. And this holds for all red paths. Therefore, priority of S is equal to the past cost of S. Okay, any questions? I'll pause a moment there. Okay. So the upshot of this is UCS is correct. You can all sleep at night and use it with cycles. It's great. All right. So summarizing UCS, it computes past costs for each state in non-decreasing order. So remember, there's a key dilemma we had. How do we order the states in which we're going to compute things? And in UCS, it's increasing past cost. We use a priority queue to efficiently find the state with the lowest priority. And that priority, as we just proved, is the past cost. And it has nice guarantees. Okay, so that's all I'm going to say about UCS. Well, directly about UCS. Actually, A star is all about UCS, as we'll see as well. So UCS works. Okay, so I really like this video, so I'm just going to play it again. So you see UCS works. It's guaranteed to find the minimum cost path. So what's not to like about it? Yeah. Yeah, so it's uniform, which means that it's exploring everything kind of without regards for where you're going. Right. In particular, these nodes over here seem like not a useful use of resources. Okay? But uniform cost search, it doesn't know about the end state, so it can't know that this is a waste of time. So what we're going to do is introduce an A-star algorithm. A-star is actually, and I'll show you what the video for A-star looks like. A-star is going to start exploring, and you'll see that it's really prioritizing this in this direction. Now, of course, it can't just immediately jump there because there's still things in the way, and you can see kind of this pattern where it starts like running in that direction and then realizes, oh shoot, there's a barrier, so then it has to like kind of almost backtrack. I mean, there's no backtracking, but it's visually it looks like it's just trying to kind of figure out how I get around this. Okay? So you might think that, well, sure, that's fine. I can come up with a bunch of heuristics that, like, maybe I can, like, put another weight on the algorithm to get it to go in this general direction. There are many ways you can hack UCS. It turns out A-star is the right way to do it. And by right way, I mean that it actually is guaranteed still to find the optimal solution. If you think about that for a moment, that's pretty cool, right? Because you can put in some heuristic, and it still has the same guarantees as UCS. In general, if you do heuristic stuff, you don't have any guarantees. But there's a few places in machine learning where you can do it. For example, when you do use proposal functions in sampling, for example, is another place. You put in a heuristic, as long as you do your math properly, it will actually work out. Okay, so let's see how this works. So UCS orders states by increasing past cost. There's no knowledge of the end state. We would like to consider, ideally, the cost from a state to the end state. That's the piece that's missing. Ideally, if I could wave a magic wand, I would say, well, I just want to explore an order of past cost plus future cost. If you're able to do that, then in some sense, you are always exploring states on some minimum cost path. So, that would be great. But of course, you can't do this because past costs you can only go in one direction, right? So if you have past cost, then the states near the start are really easy to compute. But the states, the future costs of those states are as hard to compute. Like future cost of start state is solving the problem. So that's not super helpful. Okay, so the idea of A-star is we're going to approximate future cost with some heuristic H of S. And now I'm using heuristic in a very technical sense. Heuristic is a function that maps states to a number, which is supposed to be an approximation of future cost. Okay, so for the rest of the lecture, you should think about H of S is a heuristic, and it should try to represent the minimum cost path to the end. Okay, and I'll show you that what the heuristic might be or some examples later. But first, let me just introduce the A-star algorithm. The star should be here. I think Markdown messed up here. It's just run UCS with these costs. So what are these costs? I take the original costs from state taking an action A, and I add this thing here, which is the heuristic at the successor state minus the heuristic at the current state. Okay, so if you think about what this is doing, I'm adding a so h represents how far I'm away from the end state, how far I think I am, not actually how far I am. So I'm going to add a penalty for how much the action A takes us away from the end state. So remember, I want cost to be small, which means that I want this to be small and this to be relative to h of s. So if I'm moving very much closer to the end state, this quantity is going to be negative, right? And if I'm moving farther away, then this quantity is going to be positive. Okay, so let's do a simple example here. So here's a line search problem. So I have a state 0. I can go left or right, and I can go to 1. If I go to the right, I go to 1. If I go to the right, I go to 2. If I go to the left, -1, left, -2, left, -3. Okay, so the start state is 0. And the successors at the start state are, I can go left, I can go right, and so everything has cost 1. So if I go left, I go to -1. If I go right, I go to 1. And I can also have an is-end function, which is 2. So 2 is the end state. I start at 0. And intuitively, I want to go to 1 to 2. But if I were doing uniform cost search, I would expand out kind of in both directions. I would go to -1, I would go to 1, I go to -2, I go to 2, and so on. Okay. So I'm going to show uniform cost search, eventually does the right thing, but it explores a bunch of states that are not really necessary. Let's run A star on this example. Okay, so I'm going to show you how A star is going to help here. So first, I need to define a heuristic function. So I'm going to define this heuristic function as 2 minus state, which means that at 2, I have I say the heuristic is 0 because I'm at the end state. At 0, I'm going to say the heuristic is 2. And -2, the heuristic is 4. If you're paying attention, you realize this actually is the true future cost. But so we'll see, I guess, in this very optimistic case how A star works. Let me actually just draw this picture so we have it as a reference up here. So I have the start state, which is at 0, and I have 1 and 2, and -1, -2. Okay, so these are the states. And this is the end, this is the start. Okay? Okay, so just have that mental picture up. So remember A star is just UCS with different costs. So implementation-wise, what I'm going to do is define a modified search problem where I pass in an original search problem and a heuristic, and I'm just going to define a search problem that uses that heuristic. So the modified search problem is going to have the same states and actions, only the costs change. So what are the successors now? So from the original problem, I look at each successor, and I'm going to modify the cost. So the modified cost is the successor cost plus the heuristic at the successor state minus the heuristic at the current state. Okay? So in particular, let me just do this as a example. So let me write H, which is the heuristic here. So remember the heuristic value was 0, 1, 2, 3, 4, right? It's trying to favor things to the right. Okay, so if I'm looking at 0 and I'm looking at the modified cost is 1, which is the other cost, plus 1 minus 2. Okay, and that should, that's going to the right. So if I'm going to the left, that's 1 plus 3 minus 2, which gives me 2. Okay, so if I go to the right, that modified cost is 0. Okay, so if I were to, let's see if I have other colors here. Okay, so in the original problem, everything has cost 1. But in the modified problem, so I'm going to use blue to denote modified costs. So this was a cost of 0, and this was a cost of 2. And you can also see, I can just fill in the rest. Okay? So notice how the costs were all 1, 1, 1, 1, which was uniform cost search. And now, because of this heuristic function, I've sort of tilted things so that things over here are much lower cost. Okay. So my modified successors are, left has 2 and right has 0. Okay. So now let's use this, run A star. What does A star do? It creates a modified search problem. It takes the search problem and a heuristic and makes this modified search problem, which is actually, it's really nice. This is a general function. It's not just for this line search. Take any search problem, any heuristic, and you have at your hand a modified search problem. And then I'm just going to call uniform cost search on this modified search problem. So in some sense, it's like a 2-line implementation here. Okay, so it immediately finds the optimal solution is go right, right. Okay, which is the correct action sequence. The only slight annoyance is that, the costs are all 0 here, which is not, this is the cost of in the modified solution, not in the original solution. So then I just have to go back. This is sort of kind of bookkeeping work where I basically go through these steps and just update these costs to the original cost. So for each step here, I remember this step has the modified cost, which is 0. And recall that the modified cost is the original cost plus the heuristic at the successor minus the heuristic at the state. So then I just invert basically this. Not invert, but just negate this. So I subtract instead of add instead of subtract to get the original cost. And if I do that, then the original, I get the right sequence action sequence as well as the original cost. Okay, any questions about A star? Yeah? So the question is, how did I define the heuristic in this example? So the heuristic is defined like this. And I just, in this simple example, I just made it up. I'll show you how you can define it in general. But this is usually a domain-specific question. Yeah, question? Okay, so that's going to be my next point. So the question is, if you're subtracting the heuristic value, is it possible to get a negative modified cost? And you're probably thinking, well, that's bad news because UCS can't accept negative modified costs. Okay, so in general, not every heuristic works. So here's an example where it fails. So in red here is the heuristic values at each of these states. In blue here are the edge cost of the original problem, and in purple are the modified edge costs. Okay, so what's going on here is this 1,000. Here's the optimal solution. Like 2 plus 1 is better than 1 plus 5, and this heuristic is bad. It's almost adversarially bad because it's saying like don't go here, and this will definitely screw up. And if you compute the modified cost, you see that you get a minus 999 here, which UCS won't even accept. Okay, so definitely you can't put any heuristic function in. And even if you think, man, this is such a great heuristic function, I thought a lot about it, it's, how do you know if its heuristic is going to work? Fortunately, there's actually a very simple answer here. The answer is something called consistency. So we say that a heuristic in A star is consistent when essentially the modified edge costs are non-negative. Okay, and h of n equals 0. Okay. Okay, so what is actually? I think. Let me check something. Just want to make sure I have the latest version. All right, it's updated. Okay, so these are the modified. It's almost like too convenient, right? This gentleman said, well, what happens if the modified edge costs are negative? And it's like, okay, well, let's make them not negative. And it turns out that that is necessary, but it also turns out to be sufficient and the right definition for A star to work. Okay, so, and h of n equals 0, that is just kind of a triviality. Remember, h is supposed to be future cost, and if you're at end state, the future cost is always 0, so you might as well make it 0. There's no reason to not set hn equals something other than 0. Okay, and the way to remember consistency is, I think it's easiest to remember this as just modified edge costs are non-negative. So you have to remember what the modified edge costs are, and that's it. Okay, so now a simple proof that shows A star is correct, meaning that it's going to define a minimum cost path if H is consistent under this definition. So the proof is, I'll just explain it in words and maybe I'll give an example. So consider any path from the start to the end. The sum of the modified costs is going to be identical to the sum of the original cost minus the heuristic at the beginning. And therefore, minimizing the modified cost is the same as minimizing the original cost if you go from start to end. Let me do an example, I think, which will make this a bit clearer. Okay, so maybe I can do this example up here. So let's see. So I have a, okay, so let me actually do it a little bit more abstractly. So suppose I have just, three, let's do 4 nodes. So here's the start, and here's the end. So this is one path. It's not necessarily even the optimal path, but just like any path. So I'm going to have costs C1, C2, C3. And then I'm going to have heuristic values. So let's say this is S1, S2, S3, S4. Okay, so the modified cost here is C1 plus H of S2 minus H of S1. And the modified cost here is C2 plus H of S3 minus H of S2. And the cost here is C3 plus H of S4 minus H of S3. Okay? So if you look at the original cost, it's just C1 plus C2 plus C3. So this is the original. And then if you look at the modified, if you add these up, what do you get? You get C1. One thing, the thing to notice is that there's telescoping sums, which means you're adding H2 and you're subtracting H2. Okay, you're adding H3 and you're subtracting H3. And H4 is 0. Okay, so what you end up with is C1 plus C2 plus C3 minus H of S1. Okay, so then H of S1 is a constant because all paths have to start at the start state, which means that for any path, the original cost, if you were to solve the original problem, is identical to the modified cost offset by this constant. So UCS on these costs is going to find the minimum of this, and that's going to be the same as finding the minimum of that. Okay? Intuitively, what's going on with the heuristic is that, yes, you're modifying every edge by some sort of weird amount, but you're doing it in a very coordinated way where once you string these up, you're sort of like undoing the heuristic as you go along. Okay? Yeah?
I'm not sure if the file on GitHub is updated because I don't see that proof.
Oh, okay.
Or I guess post-lecture.
Okay. It's not updated. Okay. Well, I'll fix it after.
Thank you.
Okay. That's weird. Okay. All right. Okay, so that's about correctness. So just to recap, if you have a consistent heuristic, as defined as follows, you run A star, you'll get the correct answer, minimum cost path. Okay, so now the question is, does it help? Because the whole point of doing this is to be more efficient. Now, in general, I can't tell you exactly how efficient it's going to be because that depends on your heuristic. But here is a way to think about it. So remember that UCS explores all states in order of pass cost. Okay? And A star is going to explore all states in increasing modified pass costs, which is going to be it's going to be the pass costs with the heuristic at the S minus heuristic at the start. So UCS will explore all the states that have pass costs less or equal to pass cost of an end state without this H of S term. And A star is going to explore all states satisfying this with the minus S term. Okay, and the minus S just reflects the fact that the modified problem, all the costs are smaller. So which means that this is a stricter definition. That means there's fewer states that it can explore, and the larger H of S is, the more efficient you are, right? Because if you set H of S equals 0, that's actually identical to just running UCS. okay? Because you're not actually getting any leverage there. In the extreme, if you set h of s equals to the future cost, then, as I mentioned before, A star explores only nodes on the minimum cost path, which is great, except for future cost is in general hard to compute, because if you could compute it, you wouldn't even bother with A star. Usually, h of s is going to be somewhere in between. And the game is always choosing the heuristic that gives you most bang for your buck in order to make it h as large as possible, but still efficient to compute. Okay, so there's another notion, which I'm just going to mention. We don't actually really need it for this class, but you might have heard it in other contexts. I'll call it admissibility. H of s is admissible when h of s is lower bound on the future cost, where h is always underestimating the future cost. Consistency implies admissibility. Consistency is a stronger notion which we'll need for A star to work in graph search. Admissibility is enough for tree search, but we're not talking about tree search right now, so you can feel free to ignore that. But I just put here for completeness in case you've seen this elsewhere. Okay, so far we've introduced A star. It's UCS with a heuristic which modifies the edge costs. And now there's a question of, how do you come up with this heuristic? We know that the heuristic has to be consistent, but that doesn't really tell you what. It's hard to check. If I just write down a heuristic, how do I know whether it's consistent or not? Okay. There turns out to be a very powerful and intuitive tool so that you're always constructing consistent heuristics. And this is based on the idea of relaxation. So who doesn't like relaxation? So just to remember, right? Suppose h of s was the actual future cost. Then this would definitely be a consistent heuristic. But that's just as hard as solving the original problem. So let's relax the problem to make it easier. Okay, so here's the winning recipe. You define a relaxed problem by getting rid of some constraints of your original problem. You compute the future cost under that relaxed problem. So for every state, you have a future cost that's respect to a different problem, the relaxed problem. And then you're just going to run A star using a heuristic, which is the future cost under that relaxed problem. So remember, H really wants to be future cost, but you can't compute it. So what you're going to do is you're going to compute the future cost of something else, which is hopefully easier to compute. Okay, so what is a relaxed problem? I'll give you some examples and then I'll generalize. So first I'll talk about through the lens of how does a problem become easier to solve. There are some cases where it actually has a closed form solution. Okay, so remember this grid problem where you're trying to go from S to E. Well, how do you relax it? What's getting in the way here? The walls. So let's just throw away all the walls. Okay? So who can solve this problem? Like, what's the minimum cost path? What's the number? 8. Okay? So it's pretty easy. In fact, it's so easy that I can just write down the closed form solution, which is that future cost of a relaxed problem at some state is just the Manhattan distance between my state and the end. So end is 4, 4. I'm at 0, 0. So I'm just going to compute the distance and the L1 distance, and that's 8, and that's it. Okay? It doesn't get any easier than that. You don't actually have to search, because if you understand the structure of a problem, then you can just write down the closed form solution. Okay, so this now you can go around and you can evaluate this, this heuristic, which happens to be a future cost at various places. So 0, 1 is 7. And indeed, you're moving once closer to 4, 4. 2, 4 is pretty close. 3, 0 is a bit farther away. Notice that the heuristic isn't perfect. Remember, so 2, 4 is, sorry, did I say 2, 4? 2, 4. 2, 4 is here, and it seems really close to the end. Heuristic says it's 2, but it's actually not that close because they have to go around. Whereas 0, I think 3, 0 looked farther away from the heuristic, but it's actually closer in the actual original problem. So the heuristic is not going to be perfect, but it is helpful. The intuition here is you're favoring states that are just closer to E. Formally, it is the future cost of a relaxed problem. And I want you to always think in terms of, whenever someone hands you a heuristic, if you can interpret it as solving an easier problem, then you get consistency for free, and you don't have to, do math. Okay, so using the heuristic, I can run uniform cost search. That gives me a cost of, this is a relaxed problem, and which gives me 8. Actually, I'm not sure why I ran on the relaxed problem, but yeah, I think I meant to run this on the original problem. I'll fix that later. Okay, so in this problem, I think A star doesn't really give you much of a win here, because the original problem wasn't that hard to solve, right? It's just kind of linear in the number of states, I guess, which is, it's not that bad. So let me show you some examples which I think give you more dramatic savings. So there are cases where you can't get a closed form. That's too good to be true. You often have to relax the problem a ton to get the closed form solution. But you can make the problem easier to do search in by reducing the number of states. So remember from last lecture, we had this limited travel problem where you're traveling from 1 to n by either walking one step or tramming, with a doubling your current position. And you can only take the tram the number of times you have tickets for. Okay, so remember that you had to define this limited travel problem, and you have to keep track of, in your state, the number of tickets you have. And because you have to keep in track of your state, the total number of states you have gets blown up, which is the number of locations times the number of tickets. So you imagine, 1,000 locations and 100 tickets, then now you have like 100x times the number of states. And dynamic programming, uniform cost search all scale in the number of states, so that's not great. So now let's come up with a relaxation. So the relaxed problem, the tram is free again. You can take as many times as you want. So now this was the original travel problem. The number of locations is 10, and I don't have to keep track of the number of tickets. Okay, so how do you define a heuristic? The heuristic is always the future cost of a relaxed problem. And so what I can do is I can just solve this relaxed problem using dynamic programming. Okay, this is actually what I did in the previous lecture. And now I can define this heuristic, which allows me to plug in any state of the original problem. And there's only one kind of subtlety here, which is that the original problem, states were location tickets, and in the relaxed problem, states are just locations. So I just have to kind of project my state down into the form that the relaxed problem takes. Okay? So here, the heuristic value at this location is the cost from going to 4 to 10 by walking or taking the tram, where I can take the tram as many times as I want. Okay? And that gives me a cost of 3. So the whole point of this is that I can solve this smaller problem. I'm just going to solve it quickly. And now I go and solve the original problem. So I could have done this using uniform cost search. That's fine. Number of explored states is 23. And now if I use A star, now it's 8, which is pretty good. Now, I can't just compare 8 and 23 because I have to also account for the cost of solving the relaxed problem, which was another 10. So it's 18, which is still better than 23. Okay. So let me just kind of summarize what I did here. So here is an original problem. I had some constraints that I didn't like or made my life difficult. Relax the problem to not keep track of tickets. I can solve this problem and use that to define a heuristic, and then I go back and solve the original problem using that heuristic. Okay, so there are a few different moving parts here, but hopefully conceptually it's clear. Maybe I'll pause and take any questions. Yeah.
If we know something about the constraints, is there a way to implement a heuristic that might factor that into account?
The question is, if you know something about the constraints, can you implement the heuristic to?
Because right now it's just like a Manhattan distance, for example.
Yeah.
Is there a way to maybe build a more complex heuristic function that takes into account constraints of the environment that you might know?
So in the first case, it was a Manhattan distance, and that was because I was using fairly, direct knowledge about the geometry of the problem. In this case, I'm not using that much. I think this fewer states approach is probably the most general, because all you have to do is reduce the number of states, and then you're solving the problem. So you're still using general machinery to even solve the original problem. You don't have to think too much about that. Now, of course, there's many ways to reduce the number of states, but that's kind of the idea. Yeah.
Is it unfair to just compare the number of explorations between UCS and A star? Because for the A star approach, we have to do dynamic programming just to get the heuristic.
Right. So the question is this unfair to compare these two? Because didn't you have to compute this heuristic using dynamic program? And the answer is yes. So this, I'm adding number explored to this count. So yeah, I did that kind of quickly. But here I get 18. Without it, it would look really good. Yeah, good question. Okay, so moving on. So here we use dynamic programming to compute future costs for the heuristic. But remember, if we have cycles, we can't use dynamic programming. So what do? So there is a solution here, which is to reverse the problem. I'll just sketch this out. In your homework, you'll be able to explore this more. So the idea is that you define a reversed of your relaxed problem. So A goes from A to B, if there's an edge from A to B, then you add an edge from B to A in the reverse problem. The idea behind reversing the problem is that the past costs in the reverse problem are the same as the future costs in the not reversed problem. Okay? And therefore, if you run UCS on the reverse problem, that gives you past costs of the reverse problem, and that's equivalent to future costs in the actual problem that you want. So it's a little bit of a trick just to get all the past costs. Or I guess get all the future costs, but while computing past costs. So maybe one kind of general thing to keep in mind is that we are introducing a bunch of algorithms. They all compute the minimum cost path from the start to an end. However, some of these algorithms also produce other things. For example, UCS produces past costs, dynamic programming produces future costs. And so what we're doing is leveraging the intermediate computations for A star. And the reason is that A star needs a heuristic, basically needs future costs or at every state, not just the end. Okay, so to summarize, we still have to run search on the relaxed problems sometimes, but the relaxed problems have fewer constraints and therefore fewer states. So they're faster to solve than the original problem. And so it's an empirical question when this is a good idea. It depends on the number of states of your original problem, the number of states of your reduced problems, how tight that is. I think the best case scenario is, when there's some constraint which is not, technically there, but most of the time it doesn't really matter. And if you're able to remove that, then you might solve a much cheaper problem that gets you like 99% of the way there, and then you let the search on the original problem do the rest. Okay, so let me go through this the rest quickly now. So independent subproblems. So here's another insight here. So suppose that you have a search problem which is solving the A puzzle. So here you have a bunch of tiles arranged. One of them is a hole, and the actions involve moving one of the adjacent tiles and swapping that with the hole. Okay, so in the original problem, the tiles cannot overlap. Okay, but in the relaxed problem, you invent your own rules. You can say the tiles can overlap. So I can just drag this 8 over here. Okay, obviously makes it a lot easier, and as a result, it actually breaks up into 8 independent subproblems. Okay, and then furthermore, in this case, but not always, each subproblem can be solved in closed form. Okay, so for each tile, I just have a number of places I need to move it. I add it up, and I get the heuristic value of this particular state. Okay, so this is generally useful when your state, in general, has a bunch of people or cars or objects, and you're trying to essentially move a bunch of things around, and there's some constraints between them. And if you get rid of those constraints, you actually get a bunch of independent problems, which then you can solve. Okay, so what's the unifying principle here behind relaxations? I showed you 3 examples here. Knocking down walls, adding a free tram, tiles can overlap. Intuitively, these are all reducing constraints from the original problem. The way to think about constraints mathematically is reducing the cost of actions from infinity to a finite value. Okay, so this is a sort of maybe a slightly strange way to think about it, but if you think about before, it was impossible to go into a wall in the grid problem. You can also equivalently think about that as it costs infinity to go to that wall. Okay? So what you're doing is saying, reducing that cost from infinity to 1, essentially. The reason I'm doing this is that it exposes a more general problem, that of reducing costs. Okay, so a relaxation formally of a search problem is a modified problem where all the states and actions and successors are the same, but the costs are now reduced or at least not larger. Sometimes it's infinity to a finite value, sometimes it's some finite value to some other finite value. Okay? So, if you have a relaxed problem and you define the heuristic to be a future cost, then this is going to be a consistent heuristic. Okay, so here's the proof. It's 3 lines. So the heuristic is, remember the heuristic here is the future cost of the relaxed problem. This is going to be no larger than the cost of a particular under the relaxed problem plus the future cost. Okay, so this is basically the triangle inequality. Let me do that really quickly. So you're at a particular state S, and you can take an action A to some S prime, and if you look at where the end state is here, right? So this is H of S prime. This is H of S. This is the cost. And so basically, H of S is essentially it's the future cost here. This is the future cost here, and I'm saying that this H of S is at most cost plus H of S prime. So one way to remember this is just the triangle inequality. And that, by the definition of relaxation, is at most the cost of, because relaxed costs are smaller, so cost of SA is the upper bound. Okay. So of course, a relaxed problem isn't automatically easier to solve. If I go around and just reduce the cost willy-nilly everywhere, it doesn't make it necessarily. So costs are generally have to be reduced in a structured way so that you can either reduce the number of states to search in, you can get closed form solutions, or you can break things into independent problems. Okay? So this is more of a kind of a mathematical framework that allows us to prove correctness. When you actually design heuristics, you should still think about these 3 principles. Okay, so one final note really quickly is if you have 2 heuristics, which one do you pick? And the answer is you don't have to pick. If you just define a new heuristic, that's the max over the 2 heuristic. That gives you a consistent heuristic. So there's a proof of this, which I'm going to skip, but it's pretty straightforward. To summarize, UCS and A-star are exact algorithms that allow for cycles, but not non-negative costs, so we made a trade here. They compute the minimum cost path. They order states by increasing past costs, either under the original problem or a modified problem. In general, UCS is, you can't do better than it, but the idea of A-star is that you can incorporate domain knowledge via these heuristics to speed up the search. And the heuristics you should think about as future costs of some relaxed problem, which is you get by lowering costs in a structured way. Okay, so that's all I'm going to talk about for search problems. Next time, we're going to talk about what happens when actions have non-deterministic outcomes, like if you roll a dice. How can you find the equivalent of an analog of a minimum cost solution? We're going to talk about Markov decision processes and policies. Okay, that's it for today.